So, welcome to the education packet. It's called Steel Bridges from Concept to Delivery. The purpose of this Steel Bridges from Concept to Delivery education packet is to familiarize you students on several aspects of the steel bridge industry. There are 6 lectures in the education packet that cover many aspects of designing, fabricating, and constructing steel bridges. Most of the lectures are targeted towards simple span bridges up to 140 feet because it is sponsored by the Short Span Steel Bridge Alliance, but there is also information on multi-span bridges. The Short Span the Short Span Steel Bridge Education Packet is a wide-ranging package of information on the steel bridge industry. It ranges from the manufacture of steel to types of steel bridges, to design resources for simple bridges and more complex plate girder bridges, to economical steel bridge detailing for efficiencies in construction, to how a bridge is fabricated in the shop and durability and corrosion protection for steel bridges, to accelerated bridge construction that reduces costs and disruption to the traveling public, to finally engineering and fabricator firms that can deliver you a high quality and beautiful bridge that is delivered to the site and placed in the roadway system. The education packet is divided into 6 lectures. This slide shows the lectures and the topics covered in this short span steel bridge education packet. The first lecture is an introduction to the bridge industry and the steel bridge industry. Lecture 1 will cover the Short Span Steel Bridge Alliance, or SSSBA, and the National Steel Bridge Alliance, or the NSBA, 2 industry alliances that support the steel bridge industry, bridge infrastructure that will present national bridge statistics and the challenges with replacing the aging bridges across the country. It will also cover different types of steel bridges and the components of a steel girder bridge. We'll finish up with how the steel is manufactured and the types or grades of steel that is used in the steel bridge industry. And finally, we will look at the benefits of building steel bridges. First, we'll learn about the Steel Bridge Alliance. The Short Span Steel Bridge Alliance is an industry support alliance that is a group of bridge and buried steel structure industry leaders who have joined together to provide educational information on the design and construction of short span steel bridges in installations up to 140 feet in length. The purpose is to help owners and design engineers with designing and building simple span steel bridges. The Short Span Steel Bridge Alliance was initiated in 2007 as part of the American Iron and Steel Institute, or AISI, where the members are stakeholders in the steel bridge industry. The alliance was formed to address 2 main concerns with the construction of steel bridges. The first is a misconception across the United States that for shorter span bridges, concrete is always less expensive than steel. The second issue is that a concrete bridge is easy to design using charts and tables. They are standardized. Whereas a steel bridge design is an individual piece of art for each bridge project. The Alliance has developed economical case studies that address the first cost and life cycle costs of steel and concrete bridges that show both steel and concrete bridges are competitive in the short span market. The goal is to break that preconception that concrete is less expensive. We will look at these studies in Lecture 2. The Alliance has also developed standard simple span steel bridge design standards for bridges up to 140 feet, so that when an owner or engineer is considering the design for a short span bridge, the steel design and concrete design can be quickly developed and compared without the effort of designing the steel bridge. We will look at these standard designs in what is called eSpan 140, also in Lecture 2. The Alliance is involved with all aspects of simple span steel bridge design and construction, including outreach and education. An example of that is this set of 6 lectures. Resources on all aspects of steel bridges, sample case studies, the simple design tool eSpan 140, which allows you to get a design for a steel bridge in a matter of minutes, a technology center for owner and engineer questions, and innovative and accelerated bridge construction solutions, and manufacturers that can deliver you a bridge. The, the shortspansteelbridges.org website is the go-to location where a user can interact with the Short Span Steel Bridge Alliance. Similar to the Short Span Steel Bridge Alliance, there is the National Steel Bridge Alliance. The National Steel Bridge Alliance, or NSBA, is a division of the American Institute of Steel Construction, or AISC. It is a national not-for-profit organization dedicated to the advancement of steel bridge design and construction. The NSBA functions as the voice of the bridge fabricators and steel mills, while also partnering with the bridge design and construction community. The NSBA's partners include the American Association of State Highway and Transportation Officials, or AASHTO, the Federal Highway Administration, FHWA, State Departments of Transportation, or DOTs, design consultants, contractors, and academia. With these resources, NSBA is uniquely positioned to find solutions to the toughest bridge challenges, including those related to cost, sustainability, and performance. The National Steel Bridge Alliance is similar to the Short Span Steel Bridge Alliance in that it supports the needs of owners and design engineers for steel bridge design. Although the NSBA addresses larger steel bridges than the simple span bridges addressed with the SSSBA. However, their functions are similar and larger than the Short Span Alliance, with resources, state-level steel bridge all-day forums, a large effort with the American Association of State and Highway Transportation Officials in the design, fabrication, and erection of steel bridges. They have standard multi-span standard designs and a comprehensive multi-span design software packet called Simon for analysis and optimal design of steel bridges. And we will look at Simon in Lecture 3. They also have inclusive design resources for the design engineer, and they coordinate the World Steel Bridge Symposium once every 2 years. And like for the SSSBA, the website is the go-to location for the National Steel Bridge Alliance. Now let's look at information on the National Bridge infrastructure. The American Society of Civil Engineers routinely rates the state of the infrastructure in the United States. For bridges, the news is not positive. Bridges received a grade of C+ in the 2017 ASCE report card, representing no change in overall assessment from 2013. Of note, significant progress has been made in reducing the number of bridges rated as poor, which were previously known as functionally or structurally deficient, but the age of the nation's bridges continues to increase. According to the American Society of Civil Engineers, it will take approximately $4 trillion to repair the current state of the U.S. bridge inventory by the year 2025. In the inventory, there are over 616,000 bridges across the United States. Roughly half of them are shorter than 140 feet in total length, what the Short Span Steel Bridge Alliance calls short span bridges. Of those, 306,000, or over 11%, are rated as poor due to condition or functionality problems. County bridges, or counties, maintain a considerable portion of the bridges in the United States, with over 152,000 in their inventory. 13% of the county maintained bridges are rated as poor, slightly higher than the 11% overall. But there is a great need to address the current bridge infrastructure deficiencies with cost-effective repair and replacement programs at the state and at the county levels. States and counties are responsible for the majority of the nation's bridges. There is a considerable difference between state and county bridges in terms of those rated as poor. County-owned bridges are in worse condition, with over double the percentage of poor bridges as compared to state-owned bridges. This equates to about 24,000 bridges and represents over half the total number of bridges rated as poor. The historic market share for steel is about 33% in the short span market, as shown on the top left circle. Steel has historically performed better in the longer span markets, as seen in the chart. However, steel's share in the short span market has steadily increased over the last 10 years as more counties and state bridge owners recognize the advantages of steel bridges. Here, the definition of the bridge lengths is culverts have a minimum length of about 20 feet. Short span bridges range from 20 feet to 140 feet. Medium span bridges mean between 140 feet and about 250 feet. Long span bridges are typically defined as between 250 feet and 400 feet, leaving the major spans having a length over 400 feet. The traditional method to build a bridge is to have the owner contract with a designer to develop the bridge design, then contract with a contractor to build the bridge. Although this traditional method is usually successful, there are times where there are disagreements between the designer and the contractor, and the owner is stuck in the middle to sort out the problems. This can cause extended delivery times and cost overruns. Rather recently, the design-build method to deliver a bridge has gained momentum and acceptance. The designer and contractor form an agreement and become a design-build team to deliver the bridge to the owner, and the owner only contracts with the design-build team. Any issues that come up are dealt with within the design-build team, which leads to a more efficient project delivery. We expect to see in 2020 the launch of a long overdue U.S. infrastructure upgrade initiative. To meet future demands and to restore the country's competitive advantage, the U.S. government has agreed in principle to spend about $2 trillion over the next 10 years, one of the biggest infrastructure investments in U.S. history. This plan to invest in upgrading infrastructure brings a significant opportunity to the engineering and construction industry. In addition to the federal budget allocations, private funding is expected to be needed, and there is an opportunity to engage in comprehensive multi-bridge public-private partnerships and bridge bundling programs to better meet the bridge replacement needs with limited funding. The Short Span Steel Bridge Alliance and the National Steel Bridge Alliance are available to provide assistance to educate stakeholders to create successful bridge bundling projects with steel through coalition building, project delivery methods, preliminary design, and so forth. Next, we will look at the different types of steel bridges that can be used to meet these bridge infrastructure needs. Because steel is a material that can be shaped and formed pretty much any way imaginable, steel bridges come in many styles and configurations. Although the education packet here will mainly discuss typical bridges for short or medium span bridges, we will first explore the many different steel bridge types and configurations. Starting at small bridges, we typically think of culvert-type bridges called buried steel bridges. Corrugated steel piping is a form of prefabricated steel superstructure that can be installed rapidly. Due to newly developed steel grades with many beneficial properties, a steel superstructure like this can be lightweight, strong, and cost-effective. This type of culvert bridge superstructure is usually for spans of about 15 feet maximum. Corrugated structural plates, also called buried steel bridges, is another steel option for a superstructure. The structural plates are formed and supported in such a way as to support the soil and roadway above with arching action. This aesthetically pleasing bridge can span up to and even above about 60 feet. Wide flange shapes are one of the most common superstructure elements for bridges between approximately 20 and 90 feet. These elements are aligned parallel to the traffic, flow under the bridge deck to support the loads of the bridge. Generally, the deck is attached to the girders in such a way to make the deck and girders behave cooperatively as composite members. While in longer spans, the weight of steel used for rolled beam bridge for a rolled beam bridge can be higher than that for steel plate girders, the unit cost of steel is usually lower for rolled members. Transfer stiffeners are not normally required for rolled sections, and simple diaphragm details aid in making rolled sections an economical superstructure. Steel plate girders are also common in as steel superstructure elements. When used in a bridge structure, the plate girders are installed parallel to the direction of traffic. Similar to rolled steel wide flange members, the deck and the girders act as composite members. The shape of steel plate girders differ from rolled sections in that rolled sections are doubly symmetric I-shaped sections, and steel plate girders can be detailed to be more efficient and are generally only singularly symmetric. This section optimization usually results in steel plate girders having a lighter total steel weight. For larger bridges, other steel superstructure types can be more economical than girder bridges. Box girders can remove the number of girder lines required for a girder bridge, which saves on formwork, end bearing, and substructure costs. A box girder is also torsionally stiff for wider box spacing, and they are aesthetically pleasing. The closed form of the box also is a benefit for durability and maintenance. Many times roadway alignments, right-of-way constraints, and congestion require bridges to be curbed or even curved and super elevated. This is not a problem with steel plate or steel box girder bridges. Steel can be fabricated in pretty much any shape or form that is required to meet the roadway alignment. Truss bridges, of course, have always been a favorite of the public because they are beautiful. They can be used for short or long span bridges, and we will look at some short span manufacturer truss bridges in lectures 5 and 6. Smaller truss bridges are used commonly in pedestrian walkways. A benefit, of course, is that the structure is above the roadway, so it can maximize the clearance underneath for hydraulic openings or traffic. Another beautiful bridge is the steel arch. Steel can be fabricated in almost any shape, including curved shapes for arches. The arch is a very efficient mechanism to support loads, and steel is a strong, stiff, and robust material, leading to an efficient design for small to large arch bridges. Suspension and cable stay bridges are the showcase bridges we see on calendars and in news articles. They are very long bridges that require coordinated load-resistant systems to span great lengths. The roadway is supported by transverse floor system that transfer the loads to longitudinal girders that themselves are supported by suspension or cables from the tower. The efficient use of the coordinated structural system allows for beautiful and very long span bridges. Steel bridges can also meet the needs for special purpose bridges. Shown here are examples of girder and truss movable bridges. For instance, when we need a movable bridge that can get out of the way at times, steel is strong, stiff, and lightweight so that the substructure, foundations, and moving mechanisms can be efficient and economical. So getting back to simple span bridges, different types of steel bridges are economical for different span lengths. The most typical, of course, is beam bridges using rolled beam wide flange beams or plate girder bridges. Rolled beam bridges are economical up to a little over 90 feet, whereas plate girder bridges are more economical at spans above that. However, fabricator efficiencies can make plate girders more economical than rolled beam bridges down to about 60 feet, so designers should consider both. Much of this education packet is geared towards these rolled beam and plate girder bridges, but we will look at corrugated structural plate, truss, and other innovative steel systems in lecture 5 and 6. If we look at the components of a rolled beam or plate girder bridge, we divide it up between the superstructure, which is everything above the pier, cap, or abutment, and the substructure. For the superstructure, we have the riding surface, concrete slab, or the deck that may have a wearing surface on top that is supported by the girders. The girders transfer the dead load and live loads to the substructure through the bearings, here shown as elastomeric bearings. Beam bridges are horizontal beams supported at each end by substructure units and can be either simply supported when the beams only connect across a single span, or continuous when the beams are connected across 2 or more spans. Multiple simple span bridges are certainly easier to design, but if the bridge has more than one span, continuous spans usually is more economical. Lecture 2 will examine simple span bridges, and Lecture 3 will look at multi-span bridges. The rolled beam or plate girders resist the dead load and live load shears and moments along the span. There are bearing stiffeners at the supports where there is a large transfer of force into the bearings and then to the substructure. Within the girder, there are transfer stiffeners welded in the section that may be used to strengthen the shear capacity of the girder, but are also there to be used for the cross-frame diaphragms connecting the girders together along the length. Here is shown a simple bent plate or channel cross-frame diaphragm on the bottom left that can be used for simple bridges. The rolled beams or plate girders are usually made composite with the concrete deck to produce a stronger and stiffer bending element with shear studs along the top of the flange, as is shown on the bottom right. We also see a welded shop splice that is built in the fabrication shop before the section is shipped to the site. This slide shows many of these components for a plate girder bridge. We can see the flanges and the webs, the stiffeners, the cross frames, and the composite shear studs. However, we also see a bolted field splice between the 2 sections that are shipped to the site. And we see that the flanges transition sizes at the bolted field splice. We will discuss these shop splices and these field splices in Lecture 3. So those were the basic steel types and steel components in a bridge superstructure. But steel is used in all aspects of bridges, whether the bridge is a steel bridge or a concrete bridge. In addition to the steel superstructure, steel is used in abutments with steel sheet piling or H-pile deep foundations, reinforcing steel in the abutments, the piers, and the concrete deck, guardrails, and even for the riding surface deck itself. Steel is a strong, stiff, and robust material, and next we will look at how steel is produced and the types of steel used in bridges. Steel is known for its strength, stiffness, and versatility. Steel making can be broken down into 3 main categories: iron making, steel making, and rolling or continuous scaling. Steel is made from iron ore and carbon from coal, with other elements added for particular properties. However, steel is also the most recycled material in North America. So much of the steel is produced from recycled steel. For recycled steel, scrap steel is melted in an electric arc furnace, shown up here on the top left, and adjusted or modified in a ladle metallurgy furnace to meet the desired chemistry for reuse as steel. To make new steel, on the bottom left, iron ore, coke from coal, and limestone are placed in a blast furnace to produce pig iron, which then typically has about 25% scrap steel added to it in a basic oxygen furnace before going to the ladle metallurgy furnace for further modifying to meet the chemistry needs. After setting the chemical composition and removing the impurities, the molten steel is ready to be turned into structural steel. Structural steel is defined by 4 different types by their chemical compositions and the steel processing methods. Carbon steel, which is the traditional low carbon steel. High strength low alloy steel, which is a carbon steel with strengthening elements added to the chemistry. Alloy steels that have additional elements added to further improve the properties, and stainless steel that has superior durability and corrosion properties by the addition of chromium and usually some nickel. The 4 different types of steel are available in many different grades with different properties, as will be shown in the next slide. For the available properties and grades of the 4 different types of steel, not only is the chemistry composition important for the grade, but so is the processing that results in the different grades. Various processing techniques for rolling and heat treating create the various grades from the 4 types of steel. This table shows the grades of steel based on chemistry and processing techniques for the 4 different steel types. Bridge steels are defined by the American Standards for Testing and Materials, or ASTM, specifications, and the American Association of State Highway and Transportation Officials, or AASHTO specifications. For the AASHTO specification showing on the left here, the number, for instance, the 50 and 50W, represents the design yield strength. Again, here, that would be the yield strength is 50 KSI of the steel material. The letter after the designation represents properties associated with that grade. Here, the W stands for a weathering steel that we will discuss in Lecture 4. Plate material is made in all the steel grades, but shapes like angles, channels, and wide flange beams are only produced up to a 50 KSI yield strength material. The designer has options for the steel material used in the bridge depending on economy, durability, and corrosion protection systems, as again we'll talk about in Lecture 4. So getting back to the making the steel, we have the product liquid steel with the desired chemistry in the ladle, and that enters the continuous caster, or I'm sorry, enters a caster. There is a continuous caster. This is not that. The caster produces semi-finished shapes that are cooled and ready for rolling into products. The semi-finished steel come in 4 basic types. There are slabs, which are wide and flat shapes that will be used for rolling plate later. Something called a bloom, which is rectangular shape for rolling different shapes. Beam blanks for rolling W-shaped beam members, and billets, which are small square shapes. These semi-finished shapes are then reheated and rolled into the desired products. This is where the processing can modify steel properties such as design strength through a process called quench and tempering the steel. The final product then comes out the back end. It is cut, treated, cooled, and packaged for the customer. For steel bridges, we use plate and rolled products. This is a sample list of the products available to us when designing a bridge. However, since steel comes with so much variety in grades, shapes, and design details, that flexibility can also be a detriment when it comes to fabrication, erection, and economy for steel bridges. Fortunately, there are guidelines for the use of steel shapes and sizes and detailing in terms of fabrication, erection, and economy that we'll talk about in Lecture 4. Next, we'll learn about the advantages of steel bridges. Every bridge material, whether it's steel, concrete, or even wood, has certain benefits. For steel, there are many important benefits. Steel is state-of-the-art. Steel's lightweight speeds construction and permits use of smaller scale equipment at the construction site. In many cases, local crews can be used to install a short-span steel bridge. Steel is lighter than concrete for the same load-carrying capacity. And steel components are made to closer tolerances being in the fabrication shop, which often translates into faster erection. Steel is also durable. Steel is highly resistant to extreme natural disasters, such as earthquakes. An example of that is the 1994 Northridge, California earthquake, which destroyed the surrounding transportation infrastructure. However, 96% of the existing steel bridges were completely undamaged, even though they were designed using 1940s technology. Steel's high strength permits longer spans, minimizing disruption to underlying habitats. In some cases, this can eliminate the need to undertake costly environmental impact studies. And steel bridges have long lives, decreasing the need for replacement. Steel aids in the speed of construction, or what we call accelerated bridge construction, which we'll talk about in Lecture 5. Steel bridge fabricators provide a wide range of modular, prefabricated steel bridge and culverts. Some can be installed in a weekend, as we'll see in an example a little bit later. While standard plans and design aids now available through E-Span 140, a short span steel bridge can be designed and fabricated in a short amount of time. Steel is also cost effective. Due to the light weight of steel, cost savings can be significant. Smaller abutments, use of local crews, fast installation, lighter equipment. When you add them all up, steel provides a significant cost savings. For corrosion protection, studies show that weathering steel reduces both initial and life cycle costs. Hot dip galvanizing, metallizing, stainless steel, and painted bridges are other options for corrosion protection that we'll talk about in Lecture 4. And finally, steel is sustainable. Steel is North America's #1 recycled material. Each year, more steel is recycled than aluminum, paper, glass, and plastic combined. A steel beam is made up of more than 90% recycled material. The energy conserved each year by recycling steel could power approximately 18 million homes. Production has become more efficient with an energy use reduction of 33% since 1990. And greenhouse gas emissions per ton of steel shipped have been reduced by nearly 45% since 1975. Also, steel from a disassembled bridge can be used again for another project. When Hurricane Ivan damaged the bridge over Florida's Escambia Bay in Pensacola, contractors used 36-inch steel beams from a disassembled bridge in Tennessee to make repairs. So that completes Lecture 1. In Lecture 1, we looked at the industry alliances that are in place to help owners and engineers design, fabricate, and construct steel bridges. We also understand the United States bridge infrastructure condition and the replacement needs. The steel production and bridge grade steels will be used in the future lectures when we discuss bridge design. And finally, we understand that there is a choice of material when building bridges and that steel has some favorable benefits that should be considered when selecting the bridge material. In the next Lecture 2, we will study the economics of steel and concrete bridges on first costs and life cycle costs, and demonstrate that SSSBA E-Span 140 standard design software for simple span bridges. If you are looking for more information, we have the shortspansteelbridges.org website, and the Alliance also uses Twitter and Facebook.